Hello, guys. We are back yet again. Welcome back to MJ School of Mining and Geology. In today's lesson, we are dealing with what you call a polymorphic phase transformation. This is one of example of phase transformations, wherein the transformation refers to a process where minerals in a rock will change into a new mineral with either different chemical composition or structural behavior. All right. So this change would always happen because of the intense pressures and temperatures that are were subjected to a particular rocks. Okay. Now making sure now that the minerals inside that rock, because now they are no longer stable. Okay, they are no longer they do not feel comfortable in that new temperatures and pressure conditions, and then they will, transform into the new stable mineral. So this transformation is driven by the need for the mineral assemblage to achieve a more stable state under the new metamorphic conditions, or under the new temperature and the pressure conditions. Okay. So please don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. Okay. So like I said, the phase transformation is just minerals being exposed to intense temperatures and pressures, and they do not feel comfortable in those conditions, and then they will be transformed into the new minerals with different structures, or it can be with different chemical composition. Okay. Because of these would be in response of pressures, temperatures, or it can be fluids. Okay. And then minerals are striving to attain the new what you call stability. They need to, be stable in new metamorphic conditions. Okay. But now today we are focusing in what we call a polymorphic phase transformation. Now polymorphs would be those minerals with the, same chemical composition but different structures. Okay. For example, when we look at the aluminum silicates, such as Andalusite, Kyanite, and the Sillimanite. They are polymorphs because they are all having this formula. Okay, they are all having this formula. And these minerals, they usually they get to, be transformed because of different pressures and temperatures that particular those minerals are experiencing. Okay. So you can now see that I like this diagram because, you know, um, okay, where's my pen? Okay, it's back. So we know that here it's Kyanite, and then here at the bottom it's the Andalusite, and here it's the Sillimanite. Okay, so what's basically is happening is the Kyanite, for example, it's high pressure. Sillimanite, it will be high temperature. And this one, it will be, we can say, high temperature, or medium to high temperature. Okay. So basically what is happening is, if you are converting, okay, or if you are in the Kyanite zone, you are just in what you call high pressure series. Okay, that's why Kyanite it's a high pressure, and then we call that a blue schist. Okay, you must know these things. Then now, if you were to convert or transform Kyanite into a Sillimanite, you are in medium pressure series, and that's what you call it the Barrovian. Okay, that's what you call the Barrovian when you are taking the Kyanite into the Sillimanite. But if you are taking the very same Kyanite into the Sillimanite, but at low pressures, then we say that it's a low pressure series and it's a Buchanan. So it means both the Barrovian and the Buchanan, they are pressure series, but the Barovian, it will be a medium pressure series, and while Buchanan, it's the low pressure series. Okay. And then we have the, the Hornfeld series with is associated with the contact metamorphism. Okay, so remember the blue schist. These ones they're associated with the regional metamorphisms. These ones they're associated with the regional metamorphism, and this one Hornfeld series is associated with the contact metamorphism, wherein the temperature is playing much role. And then if you're converting this kyanite into the Andalusite, you are in what you call the Hornfeld series, or you can have the Andalusite into the Sillimanite, you are in Hornfeld series. Okay, so can you now see that indeed at high pressure you are in what you call kyanite? Okay, the kyanite is stable and it's comfortable in a high pressure zone. Okay, it's comfortable, it's stable in that zone. But low pressure, stable form is Andalusite, because if you can check, pressure is here, somewhere here. Okay, Andalusite, it's a pressure, it's a low pressure. Okay, a stable form of this aluminum silicate or aluminum silicates. Okay, but now the high temperature it will be sillimanite. If you can check, sillimanite it's occurring at high temperature, so it means sillimanite it feels comfortable when it's under the high temperatures. So this transformation is due to the fact that if the if let's say you are in the low pressure series, okay, Andalusite, for example, and then what you are doing is you are increasing the temperature. You're gonna cause the Andalusite to transform into a Sillimanite, because Sillimanite it's comfortable, okay, or is stable under the new temperature conditions, high temperature conditions. Okay, so it's kyanite, it's Andalusite, and it's Sillimanite. Andalusite is low pressure, kyanite is high pressure, and then Sillimanite is high temperature. Okay, so all these things, all these minerals, aluminum silicate minerals, we call them the polymorphs. They've got the same chemical formula, but they are different structurally. Okay, so which is why we say in the okay in different structural forms over pressure temperature ranges, similar to what is happening with water. But you're gonna have liquid at room temperature, but if you try to boil that water using your kettle, then you're gonna transform the liquid into or basically let's start with the what's happening in the fridge. You're gonna be having your ice, okay, in the fridge. But if you take that ice out to the room temperatures, the ice will melt. Okay, so can now see that, oh, you've changed the conditions. In this case, you are changing the temperature. Ice is comfortable inside the fridge. That's where it's stable. That's why it's in icy form in the fridge. It's stable. But now, if you are exposing that ice to a new temperature, okay, that is room temperature. Okay, now that ice will melt and then it will give us the liquid. Then the liquid will be, um, um, comfortably inside the Jojo tank. You'll be able to drink and do whatnot with that. Okay. But now immediately when you take that water and put that into your kettle, and then you switch your kettle on, then the water will start to gain what you call kinetic or sufficient kinetic energy. You'll see now the water particles will start to now jump. The water molecules will start to now jump because they received sufficient amount of energy. As they're doing so, they will be attaining high temperatures. Okay, then now with time, the liquid it will be converted into gas, because now the liquid it's no longer stable under extreme temperatures that are being caused because of the because of the kettle being switched on, then that will be converted into the gas, and then gas, it will be, a new phase which is stable under those extreme conditions. Okay, so basically that's exactly what's happening with this kyanite and sillimanite and andalusite. So and there's Andalusite here. It will the type of metamorphism, it will be what you call the contact type metamorphism. And why is it contact metamorphism? Because in contact metamorphism, the temperature is the one which is playing a role. It's higher. But if you can check over here, the temperature is higher. The temperature is higher for this Andalusite. But now the pressure is not playing a major role in during the contact metamorphism. Okay. So the pressure is not taking place, which is because if pressure were taking place during contact metamorphism, then we were going to experience what you call the foliated rocks, or the minerals were going to be, or sheet silicate were going to be aligned in a preferred orientation. And but what we have seen in lecture 2, wherein we're dealing with foliated and foliated rocks, you'd have seen that the rocks formed by contact metamorphism, they are granular, they are not foliated because the pressure it's low, which is why andalusite usually it's typical of what you call the the contact type metamorphism. Okay, which is why it's associated with what you call the Hornfels facies. Okay, but now the kyanite and sillimanite, they would typically be of regional. Okay, they will typically be of regional. Okay, so let's try to answer these questions and then see if we really understood this polymorphic transformation of the aluminosilicates. So the first question is, what do the fields labeled A, B, C represent? Okay, so you'd agree with me that here it's a kyanite, here it's a sillimanite, and here it's the Andalusite. Okay, but I was supposed to write this here. So here we are having our kyanite. Okay. Is Andalusite a low or high pressure phase? Relative to kyanite, we are comparing Andalusite to kyanite. So kyanite, we know it's a high pressure, then Andalusite it's a low pressure. So this would say it's a low pressure phase. Okay, it's a low pressure phase. And then is Andalusite, no, it's Sillimanite, a low or high temperature phase relative to Andalusite. We are comparing the Sillimanite to an Andalusite. So Sillimanite is a high temperature phase. It's a high temperature phase. Okay. What are polymorphs? Give the chemical formula which suits all the phases. Okay, you mentioned in one. Polymorphs are, are those minerals which are having the same chemical formula, but structurally they're different. Or you can say polymorphs are minerals with the same chemical composition, but different structures. And we have aluminium 2SiO₅. Okay. In series, a kyanite would change into a sillimanite somewhere in amphibolite facies. Okay? Somewhere in amphibolite facies. I've showed you the diagram wherein the kyanite is being, converted or transformed into a sillimanite here. Okay? And then we have seen that transformation that was happening over here, that we've got transformation here, which we call it a medium pressure, and we also have got the other one here, which we call it a low pressure. So a medium pressure, I told you that it's what you call a Barrovian. A Barrovian, and this one is what you call Buchanan. Sorry about my handwriting. So in phase, A would be changed would change to be in somewhere in amphibolite facies. So this would now be the medium pressure series, which is what we call the Barrovian Barrovian facies series. Which aluminosilicate polymorph is associated with a very high geothermal gradient, such as might be expected in vicinity of intruding magmas? What is the type of facies associated with that? We know, I've already mentioned the fact that if we have the non-foliated rocks, or the non-foliated rocks, wherein we have got the minerals which are tightly packed. If we have got the minerals which are tightly packed, it's a typical of the contact type metamorphism. So the type contact type metamorphism, sorry, is the type of metamorphism associated with the intruding magmas. Okay, and now that is happening somewhere here. Okay, so the type of okay, what is the question? Which aluminosilicate is associated with which aluminosilicate? The aluminosilicate, it will be Andalusite. Okay, one. Okay, because of Andalusite is happening in conditions wherein we are having low pressure but high temperature. What is the type of facies associated with this aluminosilicate? We know it's the contact. It's the contact or on fells facies. Okay. Okay. So at what conditions of geothermal gradient will a kyanite be converted to Andalusite? And this, so it's like, let's make it like that, and then our, so it's something like you. So it's fine. Let me just wrap here. Let me erase everything. Yeah, it's fine. Let me erase these ones. Okay. So it's like the question asks, what conditions of geothermal gradient will kyanite be the first? Kyanite will be converted into Andalusite, and then the Andalusite could get to be converted into Sillimanite. Okay, this would need a slightly higher geothermal gradient. Okay, it would need slightly higher geothermal gradient. Okay, this would need slightly higher geothermal gradient to be able to produce this kind of succession wherein kyanite is converted to the Andalusite, and Andalusite is converted to what you call the Sillimanite. Because remember, kyanite is high pressure. So if you if you're increasing the temperature, now this one, it will now have the Andalusite. It will now be converted into Andalusite, because Andalusite it's at high temperature as well, but not as compared to that of the Sillimanite. Okay. But if you were to look at pelitic rocks, such as the mudstones and shales, okay. So if you were to look into these rocks, the mudstones and or mud rocks and shales, these types of rocks would show such a change in the aluminum silicate minerals, okay, from the kyanite to the Andalusite, and then Andalusite to Sillimanite, okay. And then this is basically what we call it what I've explained earlier on as the Buchanan or low pressure series, okay, low pressure series. So can you now see that, okay, each series, it has typical, is described by its typical geothermal gradient. Okay. The intruding magmas would be that of Andalusite, okay, during intrusion, but during regional, usually the high pressure, kyanite. But now, if we're looking at the rocks such as shale, remember shale in lecture 2, for example, we've mentioned the fact that it contains clay minerals and a bit of quartz, so these minerals, they're having this aluminum, they're having this aluminum silicate. So this rock would, if you expose them to the slightly higher geothermal gradient, they would tend to be converted into the Andalusite, and then they become stable. Then you keep on increasing the temperature, then this will be converted into the kyanite. Okay, so if you can still remember at that Buchanan series, okay, it's somewhere here. It shows that now you can convert the kyanite into the Andalusite, and Andalusite later into the Sillimanite. So basically, that is that, good people, about the a polymorphic transformation. This is example of the this example of what you call phase transformation. We have other things like recrystallization, neocrystallization, and many other things. But today we're specifically focusing on what we call the polymorphic transformation. I hope you've enjoyed the session. If you haven't yet subscribed to our content, you are more than welcome to do so. Please like and hit the notification button below so that you are notified each time we upload new content. But to show support and appreciation, please share it to the other people who do not know the MG School of Mining and Geology YouTube channel, wherein we are striving hard to promote the academic excellence. It doesn't matter whether you are you know a seasonal geologist, or you just curious to understand the concept of geology, or whether you're a student or whether you are an academic staff. We are trying to simplify the geological complex into a simple and understandable concept. Okay, so thanks for joining us. Our next lecture, it will be on the what you call the textural equilibrium, and then we're going to be explaining basically what's happening during contact metamorphism, why this textural equilibrium is only taking place preferably during the contact metamorphism, why this is so special during the contact type metamorphism. Why is it not happening during regional? Why is it not happening during a dynamic or shock metamorphism, or many other types of metamorphism, but specifically contact metamorphism? Okay, I always like to say, until next time, cheers.